Hi there, this is Module 5 Video 33. In this video we're going to build a numerical constraint parser. So in order to explain what I mean by the numerical constraint parser, you may recall this example exercise document that we saw in the slides at the start of this module. So I'm just going to simplify this a bit so that we can concentrate on the important bits here. So this thing here, before set 2, this 2 here is what is one example, the simplest example of a numerical constraint. Obviously each set has a number, and in this case we only want to execute the actions here if the set number is 2. So this particular constraint I'm going to call a literal constraint, because obviously you're constraining against a literal number. It could equally be 1 or 45 or 4, whatever. The next type of constraint that I want to make sure we support, I'm going to call a symbol constraint, where you've got the option of using one of two symbols. You can either say first, which is basically a pseudonym for 1, or you can say last, which is a pseudonym for whatever the last set number is. So obviously here last is more useful than first, but first is good to have there just for consistency and readability. So here we're saying execute these actions only before the last set. Now the next thing I want to support is symbol expressions. So not only can you say last, you could say last minus 1, which is second to last set, or last minus 3, or you could say first plus 2. I'm only going to support plus and minus here. No division or grouping operators or anything too technical. We just want to make the first and last symbols a bit more useful. So that is a symbol expression. In addition to that, I want to make sure we support ranges. So you could say 1 dot dot 3, which means 1, 2, and 3, or 2 dot dot 5, so 2, 3, 4, and 5. So these are inclusive ranges. The other thing you could do is specify a jump, a number of items to skip in between. So this is set number 1, 3, 5, 7, 9, because we're specified to take every second set, or every second number rather than every number. And equally, this could be every third number, every fourth, etc. Now, in addition to that, we can combine these concepts. So we could say before set first to last. So that means before every set. So that's not very useful. But you could say before set first to last minus 1. So that's every set apart from the last. Or you could even do plus 1 to minus 1. So that's every set apart from the first and the last. There's other ways of expressing this, as we'll see shortly, but you could also have something like this, where you're doing every second set. So that's ranges, and then on top of that I want to support mathematical sets. So I'm being careful here to call it a mathematical set so we don't get confused between an exercise set and what I would normally just call a set. So in a mathematical set, usually it would be written something like this, 1, 3, 5, 8. So this is all the this would match on any set as long as its number is 1, 3, 5, or 8. But for the purposes of our exercise document, I'm going to be slightly more lenient with the syntax and just allow something like this, so it's less technical and easier for the average Joe to kind of use. And all the concepts we've discussed up until now are also applicable to sets. So you could have, instead of 1 here, you could say first, and you might want to use a mathematical expression as well. Sorry, a symbol expression as well. And you can even have ranges within your set. So you could have 8 through, or 9 through 15, like that. And the order here is not important. It doesn't matter if you know if it's 5-8 or 8-5. That's not important. Now finally, to top it all off, I want to be able to specify logical not or a not in operator. So you can do something like this. That just means every set apart from number 1. You could say the same thing in this way, or you could say every set apart from the second to last one. Every set not in 1, 2, or 3. And finally, you could also use the not operator with a set, a mathematical set. So you could do something like this. So whenever the set number is not 1, 3, or 5, then that matches. Now you may expect this to be not 1 and then 3 or 5, but that turns out to be a bad idea because it can lead to situations that just don't make sense. For example, you could have for set 1, not 1. What does that even mean? We probably don't want to allow that. So I've got kind of an implicit parentheses around the set here, or maybe it would make more sense to do it like this. So this is any set that isn't 1, 2, or 3. However, like I said, I kind of want to simplify the syntax. So it's a bit of a trade-off here between complexity and readability. So I'm not requiring these parentheses here, but this not operator applies to the whole set that follows it. So those are the specific scenarios that I want to support with our numerical constraint parser. So let me just quickly create some classes and then we can talk about APIs and what have you. So the API for the numerical constraint parser is going to be a bit more complicated than what we've had until now. You may expect it to look something like this. Where we're kind of getting a parser of Boolean and it tells us whether a number matches that constraint or not. However, this is not sufficient because if you imagine our constraint is simply this, before set last, or actually last is the constraint. How does it know what last is? When you get the parser, how can it possibly figure out whether it's going to match or not, unless you can give it both the number of the current set or rep and the number of the of the last set or rep. So that's not going to work unless you get a parser every time the set changes or the rep changes, which obviously is just not feasible. And we need to be able to parse before the exercise is even running, obviously. So that doesn't make sense. So we need some kind of way of knowing what the current number is, whether it's the number of the set or the number of the rep. That kind of doesn't matter to the numerical constraint parser. What it cares about is getting that number. So we're going to have to take a function that is given the execution context and returns that number. So get the current number. And instead of returning a Boolean here, we need to return another function. And that function can take the event, which we'll call t here, and it will return a Boolean that says whether it matches or not. And obviously we need to define t here, and we need t to be a numbered event so that we can actually extract the number, the current number from that event. Because remember, a numbered event has the number, whether it's a set number or a rep number, isn't defined here. But knowing that we've got a numbered event, we can extract that number. So that is the API, except we also need a way of getting the first and last numbers, because again, we don't know whether we're dealing, in this context, we don't know whether we're talking about the first and last set or the first and last rep. So we need the caller to be able to make that decision and to be able to extract that information for us. So we're going to need two other functions, and we're going to call them get first and get last. And you may think that get first is a bit superfluous because, I mean, the first number is always going to be 1, and I agree. But I just wanted to, be more consistent and, give us the flexibility later if that turns out not to be true. So that's the API. I'm just going to return null here. And now I'm going to write some tests, and I'm probably going to stop for each test and explain it because I'm going to break it up into those scenarios that we discussed, with the literals, symbols, symbol expression, ranges, sets, and mathematical sets, and the not operator. So let me start first with the easiest case, which is a literal. Okay, so here's my test for literals. We've got, first of all, we're taking the input to parse, and then we're specifying explicitly what the current first and last numbers are, and then we've got this expected, which gives us the expected result of applying that function that we get back from the parser. So first of all, we get the parser, and I'm just using before repetition event here. It doesn't actually matter what event we use, as long as that event has the proper number assigned to it. And then in order to get the, for the 3 functions that we need to pass in, I'm just passing back these values as provided by the test case. And then we're parsing the input, and then I'm applying that function that we get back to a new before repetition event. I'm just giving it a new execution context because we don't really care about that either. It's just as long as it's not null. And then I'm then I'm passing in current as the number to use for that before repetition event. And then we're asserting that the result we get back from calling that is equal to the expected value. So the test cases here make it a bit clearer. If we're parsing 1 and the current number, whether it's a set number or repetition number, is 1, and the first is 1 and the last is 4, then of course we expect that to be true because current is 1 and we're looking for 1. Similarly for 3, and if the number we're looking for is 3 and the current number is 2, then obviously we don't expect that to match. And we could do another one here just for completeness. If it's 2 but it's expecting 2 but it's 3, then we don't expect that to match either. So that is literal tests. So now let me do tests for the symbol cases. Okay, so the body of the test here is the same, but instead of passing in numbers for the input, we're passing in first or last. And if the current number is 1 and we're looking for first, then of course that should be true. And if the current number is 4 and the last number is 4, then of course we expect that to be true. Now I've also tested for the case where we've only got one set or rep. So here the first and the last is 1 and the current is 1. Then both first and last should match. And then we've got the negative cases where you're looking for first but the current number is 2. That should not match. And looking for last, but the current number is 3 and there are four sets or reps, then that should not match either. So that is the symbol case. So now I'm going to do the symbol expression case. Okay, so again the test code has not changed, just the input has. And I'm testing, the weird case where you've just added or subtracted 0 from the symbol. And then I'm testing the +1, -1. So in this case, the current set or rep is 2, so first +1 should match. And similarly for last -1, the current set or rep is 3, and there are 4 in total, so that should match. And I've got the same thing for plus and -2, and then I've got some white space checks here. And then finally I've got some negative cases here, so we're looking for first +1, but the current one is 1, so that shouldn't match. And similarly for last. So that is symbol expressions. So now I'm going to do ranges. Okay, so for ranges, again the same test code, and I think that will be the case for all tests. But there are a lot more cases here that I need to test. So I'm doing the obvious, or the straightforward case here. A range of 1 through 3, both 1, 2, and 3 should all match that. And let me just add a negative case here for 4. And then I've got a range of 1 through 5 every second item, and I'm asserting each and every number in that set. So 1, 2, 3, 4, 5, and we expect it to flip between true and false. And then I'm doing similar thing but with symbols and symbol expressions, and doing white space checks, and a simple negative case down here. I may add even more, but I'll probably do that as separately to this video in a separate commit. So that is range constraints. Now I'm going to write some tests for sets. So for mathematical sets, which I will actually call out here in the signature, mathematical set, I've got the simple set of 1, 2, and 3, and I'm testing 1, 2, 3, and 4. And then I've got another negative case here. If it's just 2 and 3, then 1 shouldn't be in that set. Then I use symbols and symbol expressions and ranges and kind of combine all those things together and make sure that we get the expected results there. And then I've got a white space test as well. Alright, so finally I have the not tests to write. Okay, so for the not constraints, doing some simple tests, not one, obviously if it's 1 then it should be false, if otherwise it should be true. And then I've got some symbol tests, and then some symbol expression tests, and then we get progressively more complicated here until, down here we've got not first plus 1, skip every second one through to last. So I've got a couple of positive and negative tests around that. And then finally I've got a white space test. So I think that's enough tests for the purposes of this video. I think I'll, after the video I'll probably go back and add some negative parsing tests where it can't even parse the input. I'm just going to skip that for the purposes of this video and concentrate on implementing the actual parser. But first of all, let's make sure that our tests fail. There we go, all failing. Now, in terms of the implementation, I think I'm going to split the primary parser, which will be returned by this method here, into several private parsers, one for each of the, or maybe more than one for each of the scenarios that we need to support. And what we can do is build the simplest one, which is the literal parser, and then return that from our public API here and see those tests pass, and then progressively add more and more support for the different scenarios that we want to support until we're actually passing all our tests. So let's start with the literal parser. Alright, so here's my attempted implementation here. We're first parsing out a number using Sprash's number parser, and then we're converting that to an int, because obviously that's just going to be a string from the input. So parsing that to an int, and then what we need to do with that int is pass back, per our signature here, we need a function that takes the t, which is the numbered event, and returns a boolean, depending on whether the event has a number that matches the literal number that we parse out of the input. So I'm taking the number that we parse out of the input and returning a function of tbool, and that function of tbool takes the event that it's given, which is the t, and calls getCurrent to get the current number from the execution context, passes in the execution context from the event, and checks whether that is equal to the number that we've parsed from the input. And that is theoretically all we need for a literal parser. So let's try the test. And indeed, we've passed all the literal tests. So let us move on to symbol tests, or the implementation of the symbol parser. Actually, before I do, I'm just going to have comments on each of these private methods to say what it is that they're doing. It's just going to make it easy once we have, you know, several of these methods here. Now, I think I'm going to break down the symbol parsing even further and have a method called getFirstParser, which returns, you know, a func of t and boolean. I'm just going to call this getFirstSymbolParser. And I think the signature is going to be very similar here, except instead of the current, we're going to need to know the first. And I've just thought of another test case we didn't actually test, so I'm going to add that first. We need to make sure that we're case insensitive as well. Okay, so ignoring the case, we'll parse first, and then we'll select an appropriate function. And I'm just missing my constraint here, which is why it's not resolving this stuff. Okay, so that gives us a means of knowing or getting a parser that finds first and then checks whether the first number according to our getFirst function, which is always going to return 1. So this is basically, you can think of this as number 1 equals the number in the current event. So let me just comment that and then basically duplicate that for last. Okay, there we go. And in this case, this is much more important, this piece here, because the last is not always a given number. It could be, you know, anything. But otherwise, the principle is exactly the same. So now we need a way of combining all these three things. So I'm just going to use OR for now. We may change this later, but for now, I can just say OR get first symbol parser or get last symbol parser. And we probably need to specify t here to get this to work properly. Yep. Alright, so hopefully now we can pass our symbol test as well. Let's try that. Yep, we are. Cool. So next up is the symbol expression. Now the symbol expression is basically going to compose together the symbol parser and then optionally, you know, some plus or minus, and then some number to subtract or add onto that expression. So let's call this get first symbol expression parser. And it's going to need to look something like this. I've forgotten the constraint again. Now I've hit a bit of a blocker here, but I just want to explain this first. So first of all, we're using our existing get first symbol parser, this one here, to parse out the first symbol, and then we're optionally parsing out a number to add. So that consists of a plus symbol and then, you know, the number to add. Also with some white space, which I haven't taken care of yet, but we'll get to that. And then based on that, I'm trying to parse out something that takes a func, something that returns a func of t ball. Now, the problem here is that first, this get first symbol parser is just returning a ball. It's not returning the actual number of the first, you know, the actual number that represents first. So I'm unable to kind of perform the addition that we need to do, the arithmetic that we need to do here to figure out whether the number actually matches. So I kind of need to change these parsers, the get first symbol parser and the get last symbol parser, to return integers rather than booleans. So I'm going to do that first and see where that leads us. Okay, so it's quite a simple change. We were doing an equality check before, and now we're just calling get first and get last against the execution context in the event. So this here should now be a function that takes the event and gives us back the actual number of the first set or rep, whatever it might be. So we should be able to invoke that and pass in the event to get the number. So this will always return 1, but that's not the case with last. And then we can perform whatever arithmetic we need to do, depending on whether the number to add is actually defined, because that's optional, right? So if it is defined, we will try to extract its value, which I believe is just .get. Otherwise, it's, you know, we're just going to add on 0. And of course, now that we've changed these methods into returning a func of t of int instead of func of t of ball, we have to change this accordingly. But first of all, let me fix these comments. And of course, we need the counterpart to this, which is the get last symbol expression parser. I don't know why this IntelliSense isn't working, perhaps because of this, but yeah, I'm pretty sure it's .get, but we'll find out soon enough. Now, if we simply change these calls here to actually use the expression version, then we should get both the non-expression version and the expression version for free, because obviously our parser here, this part here is optional. So if you don't specify a number to add or subtract, then we're basically getting the original symbol parser for free. So I've not done white space checking here yet, basically because I think I might write a helper parser to do that. So let's try the test anyway. Okay, so it's not building. Right, so I need to explicitly pass through type t here. Cannot implicitly convert type int to bool. Of course, because I'm just adding the numbers here. I'm not actually checking that whole thing, whether that equals the number in our event. Okay, so that builds now. Let's try the test. Okay, so the failures here are not all white space tests. This one's failing here for some reason. Last -2. Expected true but was false. Interesting. That should be working. Same with this one. So last is not working simply because I'm an idiot and I added instead of subtracting. Let's try that again. Okay, yeah, that's looks like it's done the right thing now. Okay, so now the only failures are with the white space tests. Now let me explain why I haven't fixed that yet. It might seem like the obvious thing to do here is to just stick in a dot token here, and what that does is allows white space around that particular parser, both leading and trailing white space. But the problem is here that white space includes new lines, so it would be nice if token had an overload that allowed you to specify what white space actually is, but it doesn't. So I'm going to write my own overload of token, which takes in another parser that tells it what white space is. And I'm going to stick that in our utility project, and that implies that we need Sprash. We need a reference to Sprash here. And I'm going to make sure it's in the same namespace so we just get it for free whenever we import Sprash, because otherwise it's just annoying. So let me do that quickly. Okay, so that's my extension method. That should do the trick. So it's exactly the same as Sprash's, except we've got this extra parameter called white space, and we're passing any amount of white space, and then the item, and then any amount of more white space after the item, and then returning that item. So that should enable us to easily fix our white space issue here, just by going parse.whitespace except our new line parser. Let's try those tests. And they are all passing now, so that's cool. This is still not particularly readable though. I think that whole thing there could be, simplified. I just don't know what to call it. It's not white space, it's almost white space. So once I think of a name for that, I will endeavor to kind of simplify that even further. And this expression here will be used extensively throughout all our parsers, so it'd be useful to have that defined somewhere in common. But anyways, that's our symbol expression parser done. So next up is the range parser. Actually, let me add some comments here first. So the signature is going to be similar to what we've already seen. I'm going to call it get range parser. And it's actually going to need to take all three of these methods, because it needs to compose all the bits and pieces that we've put together so far. So it needs to know about all of them. So with a range, as you saw earlier, there's either 2 or 3 numbers separated by 2 dots. So we can't assume that there's 3. So we're going to need to do some optional parsing of the third number. So let me just start typing here and see where it leads us, because I'm not really sure how this is going to look quite yet. But we know we need a first number, so let's just call it first, because we don't know. It could be a symbol, so I don't want to call it first number because it's not necessarily a number. Actually, already I feel like we're missing a building block here, because what we need to parse here is either a number like a literal or a symbol expression. And we don't currently have anything yet that composes those pieces together. So I don't want to write that multiple times, because yeah, that would be ugly. So let's write something that composes those pieces together. So we're also going to have the problem, I can see already, that once we've parsed out the bits and pieces that we need to define the range, we're then going to need to know the actual numbers in the range. What's the first number, what's the last number, and possibly what's the middle number. And these parsers that we've written here aren't going to tell us that. They're just going to give us back a boolean, not the actual number. So just like we did earlier with these ones, we're going to have to change this to return the integer. And then what we can do is compose this, this, and this. Maybe not that one. Well, maybe we'll change this one as well to return the integer. In fact, looking at this, if we weren't doing this equality check here, all we would actually be doing is returning this from this point onwards. So we wouldn't even need to return a function. All you're doing is parsing a literal number from the input and returning that number. So this would become much simpler. And then these would be returning ints. So we could compose those functions into another function that just returns the int. And that int, of course, at that point could be from a literal, or it could be from a first or last expression. And then we can take that and we can compose that further to return something that actually does the equality check against the number in the event. So we've got all our building blocks that way. We're not, because what we've kind of done here is done too much in the one parser. And so we're having to either repeat ourselves all the time, or we need to break this down further and come up with better building blocks. So let me take a stab at that. The hardest part about this is actually naming it. So I think I'm going to call it just get number parser of t, and it's going to need to know the first and last, because it's going to be composing together those parsers that we've already written, as well as the literal parser that I've just changed here into a parser of int. So what we're going to do is call that first, and then compose it together using OR with our get first symbol expression parser. And then again with our get last symbol expression parser. So that will give us a function that returns the actual number in the input, whether it's a symbol or not. So now we can compose this even further by creating a parser that returns a func tbool, and again, I don't know what to call this. Get number, maybe get number match parser, because it's matching against the current value. I really don't like this name, but it's the best I can come up with right now. And in this case, we also need to know the current value, because that's what we're going to be matching against. Let me format this so you can see everything. And of course that needs to be constrained like that. So what we can do now is call our getNumberParser. In fact, I'm going to use this kind of syntax from, I'll call this getNumber because we're getting back a function, not the actual number. And then we can select the new function. You guys are seeing the crazy things here that Xamarin Studio is doing to me. It's driving me nuts. Why? Why? Okay, so we're getting our number using the parser that we just wrote here, and then we are checking the current number against that number to get our end Boolean result. And again, I hate the names, but that's what we have right now. So let's continue on with our range parser and see if we can get any further here. So the whole point of that was to get the actual number, so now we can use our getNumberParser, and that will give us a function. So I'm going to call it getFirstNumber. So the second number, we're starting it off with the 2 dots as expected, and then we've got any amount of white space around that. And then we're calling getNumberParser. Again, I'm just wondering whether we should restrict the second number. Yeah, originally I was intending on making the third number here optional, which means that the second number could be either the last number in the range, or it could be the skip, you know, the amount of skip ahead in the range if the third number is also defined. I'm just thinking we can make this optional and make this, no, that wouldn't work. No, forget it. We do need to make sure that the third one is optional. So that would look like this. Okay, so now we've got a hold of the 3 numbers that defines the range, and this second one, perhaps a little unorthodox, but you can still use symbols in that, so you could say something like that, which really doesn't make any sense, but it's still possible. So that would be the range from 1 to 19, and every second item, because first plus 1 is 2. So it's a bit odd, but it's, you know, I can't see a way around that easily right now. So now what we're going to need to do is actually loop over those numbers and perform the actual logic of our set parser. So we know we're going to need to select a func of tbool. You know what, I'm just going to leave this poorly formatted because Xamarin Studio is just going to change it on me all the time, and I'll fix it up once we've actually passed our tests. So essentially what we need to do here is we need to loop over from the start to the end and then skip whatever we've been told to skip. So that means we need to know the start index and the end index and the skip count, which we can do in this kind of fashion. So start index is going to be get first number and then pass in the event like that. Now the end index and the skip index or skip count are contingent upon whether the third number is defined or not. I think this logic's going to be easier to do here. In fact, we can move the definition of the start in there as well. So we can just say start equals get first number. Well, you know what, let's call it get start just to be consistent, where we're getting a function here. GetEnd is going to be either the getThirdNumber optional thingy, or if there was no getThirdNumber, then that means the end of the range is defined by getSecondNumber. And getting the skip is similarly dependent upon whether the third number exists or is defined. If it is defined, then we know that the second number was the skip. Otherwise, we know that the skip should just default to 1. In other words, we want to define our own function here, which just always returns 1, like that. So now to get the start, we can just say get start e, and to get the end e, and to get the skip, we can just use get skip of e. And then we can essentially do our loop from the start to the end, and then add on the skip count each time. And now we finally get to the real crux of the matter, which is to check whether getting the current number for whatever event we've been given, sorry, we need the execution context there, is equal to I, and I is one of the numbers in the set, of course. And if it is, then we're in the set. Otherwise, if we go through all those checks and we don't find any matching, then we are not in the set, so we can return false. That is the general gist. It doesn't look like it's going to build because I've got a comma there instead of a semicolon. And also we probably need to check that the start index is less than, well, it doesn't really matter. It just means if you specify a range of 3 to 1, like that, that's essentially an empty range. And that's fine, that makes sense. We could add a test for that. So if I say 3 to 1 and the current number is 2, then that should be false. Right, so now, theoretically, assuming this works, we're going to need to compose together our range parser. It doesn't look like this is even close to building. Let me fix any build errors first. I've got to change these. And I forgot my generic constraint here. Actually, we can simplify this even further. We don't even need type T anymore. So we can get rid of that. Okay, so the problem is this getLiteralParser is now returning a parser event, and we're not converting that somehow to a parser of func of T event. So all we need here is a select, and we can just return a function that always returns that value. Like that. So the problem here is the utility method I wrote is assuming that both parsers are of type T. In this case, our first parser is of type INumericalChar, and our second parser is of type char. So it's not matching on this overload here. What we actually want to do is allow any type of parser for the white space. We just don't care because it's just well, I mean, we called it white space, but it actually could be anything. But the point is we don't care what it is, we just want to discard it. So if I change that to like that, then it will resolve that method and we are good in terms of building. So let's try the test. Actually, no, I can't try the test yet. I just have to re-enable this and fix this up. So now what we can do is we can either parse a range, and if that fails, then we can use our get number match parser to match anything else. So let's write that out. Get range parser, or get this parser. Okay, so let's try the test with that. Okay, cool, that actually worked. All the range stuff works. So that's good news. So next up is support for sets. Just let me fix up some comments and formatting here. Right, so our set part, or mathematical set parser I should call it, is going to take essentially this, any number of these delimited by commas, because this will give us, either a range or any of the components that we care about. And I think I'm actually going to, I'm going to extract this into another method and call that get atom parser. Let's go with that. Get atom parser. And for some reason it is not generic. Why is that not generic? Don't know. It should be. So it hasn't extracted the right type either. Like that, and now we can use this as a building block for our mathematical set parser. Okay, so parsing any number of atoms delimited by commas with optional white space, and then what we can do is take them and we need to convert them into a function like we have done elsewhere. And that function can basically loop over those atoms and check each one, and if it matches, then we've got true, otherwise we've got false. I could write this as using link with an any statement, but I think I'm just going to be a bit more explicit for now, just to make sure it's easy to read. So the atom here is a function that takes our event. So if that matches, then we know something in the list has matched, in the set has matched, sorry. Otherwise we know nothing has matched, in which case we can return false. It does not like something here, but I'm not sure what that is, so let me build. Oops, I forgot my T here, and also to constrain it. In fact, I'm missing that here as well. So now we can just return our mathematical set parser as our primary parser and try our tests. And surprisingly, it actually works. Everything now is done apart from our not support. So that, let me just format this. And what we can do for that is just, we could almost just stick it in here, but then we're not, it's not technically part of the mathematical set, so I'd rather have another function that kind of composes our mathematical set into an even higher level, which would be, I'm just going to call it the expression parser, because this is the top level of our parsing capabilities. Right, in this case, so what I've done is I've parsed out an optional caret, which represents a not, followed by any amount of white space, which, you know, could be good or bad. I'm not sure if I actually tested for that. Yes, I did. So you can have white space after the caret. And then parsed out the mathematical set. And so what we can do is evaluate the set. And if the not is defined, then we can essentially just invert the result that we get back and then return it. And that expression parser can be our base parser. So let's try our test. Okay, I've got a build error because I've forgotten the type constraint. Still failing. Okay, I think the problem here is we're expecting white space when actually what I want is many. I was getting confused because I'm used to using token, but I don't want to use token here because I haven't allowed white space. I don't want to allow white space before it, at least not from this particular parser. We'll be doing that, I think, at a higher level than we should be doing here. So let's try that. Excellent. So all passing. I need to go back and format this stuff and add some more comments, but actually that's by far the hardest parser we'll have to write, I believe. And incidentally, you may have noticed a bit of a difference, a bit of a departure from the other parsers in that we're not parsing out model objects here. In fact, we're not really parsing out objects at all. We're parsing out functions that encapsulate logic that will be used by our by the execution of the exercise program. And this is the piece really that gives us so much, will give the user so much flexibility in how they specify their exercise programs, that it's important that we get it right, and it's important that we have all this flexibility in syntax. And I think we've achieved that here. Obviously, as I say, I'll need to add some more tests, add some more comments, etc. But for the most part, this is done. So I will catch you in the next video. Cheers.